today's session is going to be all about quantum computing. And I'm your host, Anush, and joining me is my co-host, Vedant. And we have an excellent speaker here, Mrs. Shalaka Verma. She's the current director for partner technologies at Microsoft, and she was the CTO of IBM Subsystems Pacific. Welcome, ma'am. Thanks for this session.
Hey, thank you folks for having me here. Folks, thank you so much for taking time out on a Monday evening. I know this is not the most convenient time for learning. However, this is the best we could manage. So, bear with us, and hopefully the recording will be available. So, feel free to go at your leisure time. Feel free to connect with me on LinkedIn and see whether you have any additional questions, clarifications, etc. In the interest of time, we may not be able to cater to all the queries. And with that, let us get going. Anush, Vedant, do let me know if you are not able to see the screen. I mean, we tested just, but yeah, just in case.
Sure.
Yeah.
Sure. Yeah. Are we good, folks?
Yeah.
Yeah. So, we are touching this upon a very exciting topic today. 1 hour will not do justice to a lot of things, but, I just want to leave you with the basics, the background, and why are we really looking at these kind of technologies to help us solve what kind of problems, right? So let us start with what we know. And we know very little of the really hard problems that matter, right? Starts from optimizing your communications, energy grids, climate controls, and to the extent of really figuring out the right chemical compositions and drug discoveries. So these are the problems that matter to us as a mankind, and however we want to know or believe that the classical computing has really helped us solve a lot of them, there is just a lot of progress to be done, and we are sort of getting, I would say, blocked by the limitations of classical computing to figure out the most optimal solutions here. Now, just to put this in the context, right? A very small molecule. I mean, I'm just going to touch base upon a very specific aspect of the hard problem, and the one that is sort of shown here on the screen is the quantum simulation of molecules. And we all know from our chemistry or college backgrounds, right? So the molecular formula or the equation simulate that on a classical computer. So all our current progress on chemical simulation is based on approximation. Just to put this in the context, as your number of atoms grow, you actually need an exponentially high power of classical computing to simulate the chemical reactions with tolerable accuracy, and we are very quickly exhausting those limits. So the more complex we get into the materials, the more we are looking at this as an intractable problem, and that is where the opportunity is. One of the opportunities for the quantum computing. I generally like to really put this in the perspective in terms of nitrogen fixation problem, right? So we use fertilizers. That's the de facto for all our crop right now, and that is really feeding us as an overall population. Creating ammonia today takes 7% of world's energy because the way we have understood the reaction, for us it is high pressure, high temperature reaction. That's the best we know because we have been simulating this on a classical computer. But we also know that earthworms do this process at the ambient temperature, apparently with extremely low amount of energy in the soil. So we know that there is a path to progress, but we don't have a way to get there using classical computing. And if we free up, if we are able to achieve that, we free up about 7% of world's electricity, which can provide electricity to all the population which probably does not have access to the electricity today. So, the way we should look at these problem statements are what is the opportunity to improve and what does that improvement mean in the larger context, right? Now, having said that, whatever we are going to talk about today is quantum computing, uh, but the quantum technologies, the way they are coming together, are not limited to quantum computing. You also have a field called as quantum cryptography, and you also have a field called as quantum sensing. And I'm just sort of putting a paper out there. This is not for share. If I share the slides, I'll take the slide out. This is just for the consumption to get us in context of what we are talking today, right? So if you look at the quantum computing market, that market is actually the smallest market today at about 33 million, but also projected as the fastest growing market. So we are looking at about 2 billion market in next 10 years on quantum computing. Fairly large size market is actually quantum sensing, and this is where your sensors, the adapters, the optical, the quantum chips, which sort of measure time, give you laser photon beams, all of that coming, right? And that market is fairly large size, but linearly growing. And then you also have a quantum cryptography market and a lot of progress. So while that market is fairly sized, and this is also will grow at a very, very fast pace. I think we are looking at least 10 times growth within next 10 years. And this will probably go hand in hand with the hardware development that will happen on quantum computing side, because the development of quantum computing side is feeding into the need of doing quantum cryptography. So it's like a catch-22 situation. But the cryptography has to sort of say a step ahead so that our exposure is limited when the quantum computing is sort of mainstream, right? So that's how this market looks like, and we are really going to focus on that yellow circle in today's talk. Now let me start with a very, very simple statement, right? So our intuition of what problems we can solve today is very misleading, and this is by no means undermining the amazing amount of progress that we have done in last 100 years. Phenomenal progress, phenomenal solutions. We have come a long way in the computing technology. However, look at this circle, right? So you have this larger set of problems that you called as NP problems. Within that, there are these, NP is basically non-deterministic polynomial problem. Within that, there is a very small subset that is called as polynomial set of problems, which I have sort of bright shade gray here on the screen. That is the only set of problems that you are actually able to solve today on classical computers. That's it. And then the whole other part remains unsolved. And that is what I meant when I said our intuition of what we are able to achieve on classical computer can be very misleading because we see plethora of solutions in the market. But we are really focused on today on that very small subset of polynomial problems. What we believe is with quantum computing, some of the other problems which are called as NP problems, potentially also going into NP hard, but some of those problems may become quantum easy. And then there are other problems which are not defined by NP, but are also as part of hard problems called as BQP class of problem. Which we think is going to be quantum easy. And then there are, what I have listed here are a set of algorithms which land in each of that problem segmentation. And what is that we probably are going to solve easily or fairly, we have a fair shot at solving on a quantum computer. So BQP is our lowest hanging fruit. So factoring problems, discrete logarithmic problems. We can also probably are going to have a good shot at Hamiltonian finding, traveling salesman problems, and so on and so forth, right? So just wanted to set that context here, right? So we are not, quantum is not going to solve all problems. Quantum is not going to be fit for all problems. And then in spite of the amazing progress that we will do in quantum computing, we will probably still be left with a set of problems that are still not tractable or solvable on that computer as well. But we are expanding our probability of solving larger scale of problems. Right? So that's how you should look at this new computing paradigm. Now, the set of algorithms that I just talked about, they are really underpinning a lot of industry use cases, like optimization kind of solution really helps you look at different use cases in different industries, which depends on that kind of solution. Like in automotive space, you are looking at vehicle routing. In supply chain or in manufacturing, you are looking at supply chain optimization. In energy, you are looking at power grid management. In finance, you're probably looking at portfolio optimization. In healthcare, you are looking at MRI or any diagnostic sequence model optimization. Right? So the moment you solve an optimization problem with more accuracy or at a faster speed, there are a lot of use cases across industry that you will directly touch. And what I've tried to capture here is those set of use cases, right? So per industry, you will have low-hanging fruits. What is green? Just an indication of the the color coding here. The green are the ones that Microsoft is actually working with our end customers to already put a solution in place. And white is what we think is a good fit on a quantum computer, but we really right now are not working with any customer to solve it. So that's how that color coding is here. Well, I'll probably share this slide with you so that you don't have to really jot down all of these things here. But this is how the use case scenario will look across industries, folks. Now moving on, how does it differ, right? So what you are seeing on the screen is really a demonstration of how classical computer is, right? So you have these chips inside your computers, laptops, servers, and in that you have got these semiconductors and transistors and gates that you have built. And at the end of the day, you are building these bits using it, and what you control is the voltage of that bits to show a state of say 0 or 1. And this is very fundamental to a classical computer. So bit is our building block, and then the entire programming logic that we have built on top is really modifying this bit to reflect the right state. And at the end of our whole programming, all we do is really read that state, and it sort of gives you an answer of what is that we were looking at. But the foundational thing here is that a bit can be either 0 or 1. So with just 4 bits, you are able to represent about 16 numbers, right? So you could say my one number is 0000, starting from that to 0001, 0010, 100, like that goes on and so forth. 1111 is your last state. So basically you're saying with 4 bits, I'm able to represent 16 numbers, but guess what? You are able to represent one number at a time. So every time you want to represent a new number, you have to change the state of the bits and then read the data, and it probably is going to give you one number, right? And this is where a key differentiation on a quantum computer comes in. So the basic building block on quantum computer, which is an equivalent of your bit, is going to be qubit. That's a standard nomenclature now in the industry. And qubit is very different from bit in the sense that it can be in 0 or 1 or 0 and 1 state. And this last portion of having a bit representation in 0 and 1 is basically a result of a basic quantum mechanics principle called as superposition, which allows you to think of a bit as if it is in both the states simultaneously. Now, we can spend a lot of time in understanding superposition, but that is not really the topic here. So what we are going to do is we are going to accept that superposition exists on quantum mechanics, and there is a way for us to have a bit in 0 and 1, both the states simultaneously. And when we measure, by definition, the way quantum mechanics operates is when you measure a bit, which is in the superposition state, the superposition, the wave function for that particle will collapse. And by that, we mean that you will randomly get either 0 or 1 state. And the randomization of that, the probability of that is something that you are going to control. So you are going to say, my answer is, if I am going to do a setup operation on my qubit in a superposition state, I am going to ensure that I am changing the probability of this qubit appearing in a 1 state or a 0 state on measurement, and then I'm going to trust that measurement, right? So all the calculations that you are going to do on a qubit, unlike your classical bit where you are deterministically changing the state of a bit, here you are going to manipulate the probability of a bit appearing either in 0 state or in 1 state depending on your algorithm. Right, so this sort of also leads you into the way why the quantum computers are essentially parallel and exponential in their nature. It is because of the superposition, now you don't need to do one number representation at a time, because all of these bits are in superposition. They are pretty much representing all 16 numbers concurrently, simultaneously. And if they are in the equal superposition, then you have got equal chance of finding them at any number starting from 0 to 50 on measurement, right? So any operation that now you will apply on a superposition 4-qubit system will get applied to all of these numbers at the same time, all of these solution states at the same time, and you will try and change the phase and the probability of each of these answers in a way where it sort of leads you to your right answer. Yeah, so this really makes the same point again, in a much more concise way. Right, so you basically need 4 bits to represent all 16 numbers simultaneously. Just to put this in the context, right, if you were to really represent those 16 numbers at the same time on a classical computer, you will need 16 4-bit registers, which is like 64 bits of your memory to represent that one 4-qubit system, and that's where that exponential power is, right? So 2 to the power 4 is 16. You are able to with just 4 qubits, you are able to represent 2 to the power 4 kind of numbers, where you will actually need 16 into 4 bits to represent this on the classical computer. Now, just to put this in the perspective, folks, if you have a 20-qubit system, the amount of solution space that this will represent is about 16 MB, which is like somewhere equivalent to your small handheld device. Versus the moment you move from 20 qubits to 30 qubits, this is exponentially rising because of the exponential power in the bits, right? So you have 2 to the power 30 kind of number energies, solution space getting represented simultaneously, which is equivalent to, or you will need about 16 GB of memory to represent this on classical computer, which is like a typical laptop kind of a machine that you have, and at 50 qubits, you are actually looking at massive supercomputers because it will go to the scale of about 16 petabytes of your storage or your memory space. And then there is this interesting number that at about 20 to 60 qubits, you are going to require more memory than that is possible to be represented by all the atoms in the universe. So 50 and 260 are really the two numbers which are sort of a key. At 50 qubits, we think that we are at the edge of the limitations of our largest supercomputers, and that is why when you see a lot of quantum hardware companies talking about quantum advantage or quantum supremacy, they are talking about a computer which is at that range, like 50 qubits, 52 qubits. That sort of comes from this fact that this is where you start exhausting the power of the classical computers. But then guess what? You also need to figure out the right algorithm and right use case to create a quantum advantage to say, given a problem statement, there is no way that a classical algorithm will be able to solve this accurate load at that speed on a quantum as compared to a quantum machine. And this is also leading to a lot of development in classical computing, by the way, because as people look at the advantage or the possibilities of quantum, they also think through about further ways of optimizing their classical algorithms. And guess what? People can come up with new, still unfound algorithms on the classical computer itself to optimize and further speed up our processes as they are available today. So you will actually see the race happening in both the ways, where a new algorithm will get developed on quantum, at the same time the classical algorithms will see a lot of optimization and efficiencies coming in. Yeah. Now, just I'm going to spend maybe 2-3 slides to spend some time on how this whole thing mathematically looks like, right? So what you see on this chart is a block sphere. Block sphere is a mathematical representation of qubit. The standard assumption is along the plus z axis, you will. So your plus z axis is your zero representation of qubit. So when you want to say that my qubit is in zero state, which means that it has on measurement, it has got 100% probability to get measured as zero, you are going to represent that as your plus z. And 1 is your minus z. And a superposition qubit is going to be anywhere on this sphere. Equally superpositions qubit is going to be lying exactly on that xy plane, which is like an equator, right? So that's how the measurements, and so all the manipulations that you will do via gates on that qubit is really manipulating this vector on a block sphere. We are not going to get into those details today, but this is just a starting point when you start reading it, right? Now, zero is not represented as only zero because it is a vector, and it is represented by a direct notation, and those direct notations I have sort of captured here on the left hand side for your reference. Now, I spoke about qubit as a basic building block. Like in classical computer, your bit was a basic building block, and we realized that using transistors in the semiconductors, right? And that's pretty much standard nowadays. However, the quantum computing space is still developing. So the qubit is an abstraction, and your entire software stack, gate logic, everything will work on qubit. But the physical realization of qubit will vary across at least for now, it is varying a lot across different developers and OEMs. So the good ones that are sort of in active research today are superconducting qubits, track time qubits, dots, topological qubits, and time vacancies. And I have sort of tried to capture different companies who are trying to realize it via different morphologies. So if you can see, Microsoft is the only company which is attempting topological qubits at this point. Google, IBM, D-Wave, and Rigetti are on superconducting qubits. Honeywell and IonQ, QCI are on trapped ions, and you see Q on diamond vacancies. Intel is trying to do something with silicon dots. So, this is a space of an active research and active development, and you will see a news coming up in these domains every other day. So good to track. Just wanted to put this in the perspective of why you are looking at so many different methodologies. Now, all of these qubits have challenges. They differ in different criterias. Like for example, one of the criteria that is captured on this chart is about longevity. So we are talking about how long the qubit can hold its quantum state. Why this is an important matrix is because the longer a qubit can hold a state, the deeper the circuit that you can run or logic, the complex the logic can be as a unit or as a packet, right? So your smaller longevity qubits basically mean that you are able to run your complex, your shallow algorithms, not 2D versus the qubits which are sort of having large longevity. But this is also going to sort of get uh, balanced out by how long does it take for qubits to change the state as with gate operations. So if a qubit is able to do a gate operation faster, then in that limited longevity, it is still able to do something much more meaningful as compared to a qubit which is going to hold a state for a longer time, but is going to take a bit longer to respond, and hence it is going to take a lot of time to just react to your gate operations. At the same time, there is this success rate, which basically talks about what is the fidelity or what is my error rate with which I am going to measure the output, or what is my what is the what this sort of decides how much error correction you are going to use and how much time are you going to spend in that error correction here, right? So all of this is sort of going to play into what becomes at the end a successful and at a market scale kind of offering from the qubit perspective. Yeah. Now moving on. Yeah. So see the qubit, right? With all the technologies that I mentioned here, and I have left out the photonic qubits. They are in the early stage, but there have been recent successes with Xanadu and quantum computer in China as well. But leaving photonic, all other quantum states exist at very, very low temperatures, which basically means that irrespective of your physical realization, you really need to take these materials at very, very low temperatures for you to really have a real computer or the logic working. And so when you see on the pictures on quantum computers, this kind of model sort of appears, which is like a chandelier kind of structure, which is hanging from the wall, hanging from the ceiling. And that structure is nothing but a dilution fridge. This is not quantum computer. Quantum is actually held at the bottom of the screen where you see it. So that's where they hold that mount, that plate finally, which is actually your quantum computer. But the whole structure is a three-phase fridge, which is that's a technology that we developed to sort of bring the temperatures down for both for our cryogenic researches and the other stuff, which we are now using here, right? So you look at how the temperature goes down. You see that the first stage uses nitrogen, then your helium at about 1 Kelvin, you are sort of reaching your outer space temperature, but it really takes it further down to few millikelvin. At about 10 to 15 millikelvin is the temperature where quantum operates. And then it is also susceptible to the vibrations, the electromagnetic impulses coming from outside world, the pressure variations and all that. That is why you will see the quantum computers mounted on the ceiling, trying to avoid the vibrations that floor can give, then encased into maybe a glass container or something like that, to shield it as much as possible from the external environment. If we are not able to be successful in creating the quantum computers which are based on photons, this will remain the way they will get consumed, and that is why this is not stuff that is meant for all data centers today, and that is why we strongly believe that at least for next 10 years, the quantum computers will get consumed from data centers, which means that the delivery model is going to be via cloud, and we will be able to send only the required code on the quantum and get the results out and do a lot of other stuff or mainstream computation on a classical computer. So the operating model of a quantum computer in the short side is looking like a hybrid model, which is going to be a good combination of a classical server, good logic running there, plus a set of microwave pulses which can go inside this dilution fridge to change the state of the qubit, and then a dilution fridge inside which quantum computer will be held, and all consumed via cloud technology. That's how the consumption of a quantum computer will look like, right, in the near future. Now, before I really get into the how you can get started stuff, just wanted to spend some time with you again, a little bit of mathematics, couple of slides, bear with me. Another important concept to know on quantum computer is while you have got the superposition state, if you have got two qubits in the superposition state, they are going to interact, or the two states of the qubit are going to interact with each other like wave. What does that mean, right? So it's how does a wave interact with each other? It creates wave interference, which means anything that is sort of in phase will add up, anything that is out of phase will subtract. Same like the waves that you see on the beaches, right? So the waves we sort of add their valleys and troughs sort of come further in onto the beach, and the other sort of get inside where they cancel out each other. Mathematically, this is represented as a tensor product. So if you want to understand how three quantum systems are going to behave together, it would be advisable for you to sort of just do a little bit brush up of your tensor product basics, so that you get this concept right. And then there is another key concept of quantum called as quantum entanglement. And what does this really say is, if you have got two qubits or two quantum particles entangled with each other, like say an electron which is having spin up and an electron is having spin, two particles have say quantum entangled with each other, then what we are saying is if those two particles are even taken away from each other for a pretty long distance, right? And if you measure one particle at one end, and if you measure this as spin up, then if you are applying the exact same measurement on the other particle at the other end, you will always get a spin down. So you are able to predict the measurement of other quantum particle, one particle in an entangled pair by measuring one, and that is fundamental to quantum entanglement. It can sound a bit spooky, but there have been a lot of scientists who have really talked through on this. There is no good way to explain this, I think, in a language. Mathematics speaks best when you talk about entanglement. And the way to think about it is, when you have got two quantum particles, and you have a system or a state that is represented by a single equation, which cannot be represented as tensor product of the two individual states. That's where you are going to say why these two quantum particles are entangled. And I just try to capture couple of such examples here, right? So say for example, you had a quantum state of 0, and then another quantum state was superposition of alpha 0, beta 1. What you are going to get as an end result is alpha 0, 0, so which means that you have probability of finding, you have alpha square probability of finding both of them in the 0, 0 state, and beta square probability of finding first one in 0 and the second one in 1 state. So when you represent this to mathematically, you are going to say my quantum state is a tensor product of 0 multiplied by alpha 0 plus beta 1. And the moment you are able to represent this as a tensor product, this is not entangled. Right? Now, think about a state which is like, you are saying that I have a quantum system where I have two qubits and my state is such that I have alpha square probability of finding both of them in 0 and beta square probability of finding both of them in 1. And now there is no way for you to sort of represent this alpha 0 0 plus beta 1 1 as tensor product of any two states. And that is where you are going to say my state is entangled. So if it is 0 0 and 1 1 kind of probability, then you are going to say my both particles in my entangled state are correlated. And similarly, the other corollary state is alpha square probability of finding first qubit in 0 and the other one in 1, and beta square probability of finding first qubit in 1 and the other one in 0, and that is your anti-correlated entangled state. This may be confusing a bit, folks, but just wanted to keep you and leave you with some kind of mathematics involved on how to identify what is entangled state on quantum computing. Right. So now, like we talked about this becoming a probabilistic game, right? So anytime a qubit is in alpha 0 beta 1 state, you have alpha square probability of finding this on 0, but beta square probability of finding this in 1. So you are, there is no one answer. You are, and the way quantum measurement has to happen then is you write an algorithm, you modify your code, and you modify the alpha and beta in a way where if your 0 is your realistic answer, that's where you want to land, then alpha becomes probably 0.9 or very near to 1 versus beta becomes very near to 0. However, on your every measurement, you have some probability of finding your qubit in one state because it is still probabilistic and you have not made beta 0, right? So you can't do one measurement and tell the answer. So for all quantum algorithms at this point, you will have to run them through repeated experiments and do multiple measurements on exact same transformation, and then measure how many times did you get 0 versus how many times did you get 1. And if your logic was that 0 is your answer, then you're probably going to, so on 1,000 experiments, you're probably going to get more than 900 or 990, more than 990 times 0 as an answer, or maybe 10, 15 times 1 as an answer. And then hence you are going to say, because probabilistically I'm landing at 0, 0 is my answer. That is how the quantum measurement is going to look like. It is never going to be one experiment, one answer, I measure it once and I give you an answer. It is probabilistic measurement, and hence you will have to repeat it multiple times to really understand what the real answer is. Hope I'm making myself clear, folks. This can become a bit more confusing here, but of the mathematics, we are now talking about how does qubit look like, right? So now all qubits are not created equal. And what does that mean? It means that every qubit, we talked about different physical morphologies of a qubit. Some qubits are going to be high in error rate and versus some are going to be low. And so if you look at increasing the number of qubits from 10 to 100 to 1000 to 10,000, if your error rate is high, there is not much progress that you are going to make by increasing the number of qubits in your quantum computer. This is fundamental challenge. Unless we get this right, there is no point in just having a quantum computer with more and more number of qubits. Yeah. If your error rate is improving steadily, then with the same 10 qubits, you are able to achieve way more things than you are doing now. And so the right path for us is to really have this error rate decreasing steadily, and hence and also the number of qubits increasing steadily for us to land at a stage where we are able to run large-scale production workloads. Now, apart from error rate, there are a lot more. So the power of a quantum computer is not measured just on number of qubits. Hence, it is measured by something called as quantum volume. And quantum volume takes into account many things. Like one of them is actually your error correction. It also takes into account your number of qubits. But like I mentioned, it also takes into account the amount of time it is going to stay stable, which is called as coherence time. It also takes into account the confidence or the fidelity with which it gives you correct measurements, the fidelity rate, the gate fidelity, the number of time it takes for you to change the gates or do the gate operations. It also depends on the coupling map, and by coupling map I mean in a quantum computing chip, how many qubits are you able to entangle with how many others? Ideally, you would like to have every qubit entangled with every other qubit, but that is not possible from the lithography with the lithography techniques available today sometimes, right? So people are trying to figure out the most optimal path of creating uh, the coupling, and that coupling is really about which qubit can entangle with which and how many, and that also results into the power that you can able to get out of your quantum computer. So all of these parameters sort of contribute into a mathematical formula to arrive at quantum volume. And now coming back to what Microsoft is doing here, right? So Microsoft looks at quantum computing paradigm in fundamentally three stages: the Horizon 1, Horizon 2, and Horizon 3. And we are working on the whole stack. So today on Horizon 1, at the start of this era, what you have is something called as NISQ, which is near intermediate scale quantum computers, noisy intermediate scale quantum computers. And at the end of the Horizon 3, we are looking at fault tolerant, universal, large scale quantum computers, right? And this timeline can vary from anywhere from 20 years to whatever, right? So depending on how much progress can we make in each of the state. Now, to start with, all Microsoft will enable the access to quantum technologies via cloud platform. This is in public preview right now, so all of you can, if you could just search Azure Quantum, you should be able to explore this as is today. Now, Azure Quantum will make access available to partner hardware, and the today onboarded partners are IonQ and Honeywell, along with Microsoft's own technologies. Right? So you have partner hardware available today. We are hoping that in Horizon 2, along with partner hardware, Microsoft will have its own quantum computer available, and then in in a Horizon 3 future, we are looking at both partner and Microsoft's own scaled quantum systems. From the tooling perspective, we have a language called as Q Sharp and a development toolkit called as QDK. It's in open source domain, so you could just download it most from Visual Studio Code as well. And then we have technology called as QIR, which means that if you have developed a circuit algorithm on a Q Sharp or a QDK, you will be able to translate it for getting consumed on any of the partner hardware that Microsoft supports on Azure Quantum, right? So you have that integration coming in from the platform tools and techniques perspective. You can develop once on Q Sharp and pretty much run it on any hardware. In Horizon 2, we are hoping for getting the expanded partner ecosystem, other tools and techniques available. And then Horizon 3 is really going to be about optimization and mainstreaming of the tools. From the services perspective, I think most of our customers and partners start with optimization techniques today, because that is what is available via a lot of solvers. And in principle, you can do a scaled optimization using classical computers with FPGA, but writing the algorithms with something called as quantum inspired algorithms that can help you realize the real benefits on a classical hardware by modified code or algorithmic approach which takes benefit of some of the quantum computing methodologies. However, we see that in Horizon 2, the solutions will be optimized, and we should start seeing the early quantum circuit-based algorithms also getting executed. And then, of course, our holy grail is Horizon 3. So on Azure Quantum, if you land, you should see two kinds of solutions available. One is what I talked to about, which is like Q-Sharp, and you can start learning this today. There is a code sample and a learning path on Microsoft Learn. There is also a GitHub repository. You could just search for Azure Quantum Katas and it should take you to the tutorial. This is all available via Jupyter Notebooks. You could start taking the code, looking at the code, modifying it, and sort of playing with it yourself. It also gives you, if you're really writing some algorithm for a quantum hardware, it also gives you an estimate of how many qubits will you need to run it in the real time. And of course, Azure Quantum makes hardware or VMs available for you to simulate instead of running it on the real quantum hardware, because you may not have that big a machine for your production use case. And on the quantum hardware side. But whatever is available, if you're able to scale down your problem, then you can actually run it on the real quantum hardware. On the left-hand side is the optimizer. So Microsoft has QIO optimizers available on. So there are multiple optimizers available. Some of them benefit by running on FPGAs, and some can run on pure CPUs. But you have got those optimizers available today, and most of them will be able to exploit something called as quantum-inspired optimization to make your classical optimization problem faster or more accurate. And this is something that you can run today. These are the low-hanging fruits for us to get into the production use cases. Just a couple of slides on why we are thinking that the optimization is a key. Maybe I'll just skip these two slides, right? Just put this in the context, folks. Like we are in the optimization, you basically convert the whole problem statement in a way where you're trying to find the trying to find the global optima. And the challenge with the current approaches are you will land at the local optima, which is like your first dot. Your solution was actually far way down, but this sort of gets fooled because it thinks that on both the sides it is like a cliff, and hence that you have already found the solution. So in most cases, you will end up looking at the first dot as your solution, whereas the best solution was way down. This happens because in the classical algorithms, the optimization algorithms, we use something called as thermal jump to see whether we are at the right optimal location, or is there something that is further optimal or further down on the energy state. And this is done by doing a jump. So now if you think about the peak, right? If the peak is high enough, then your jump is not going to be sufficient for you to cross the boundary. And the quantum-inspired algorithms basically circumvent this problem by doing something called as quantum tunneling. So instead of trying to jump this peak, the algorithm tries to mimic walking across. So if your peak is slim enough, it can be high as much as possible, but if it's slim enough, then your chance of passing through that tunnel is high, and hence for you, your chance of finding the more optimal solution is high as compared to the classical approach. And this is why a quantum-inspired algorithm will benefit even on a classical computer by just changing the way you write your logic. Yeah. So if your solution space looks like the first one, which is like even solution space, and you are probably going to have just one global optima, your classical computing is actually going to be very optimal and good enough for you to find the answer. However, if your solution space looks like what is on the right, where you are going to have many peaks and many volume values, and you are going and the challenge is to really find the deepest value in all of these values. and that is what is called as the rugged landscape. This is where the quantum inspired algorithms will help you a lot. So yeah, so we're coming to the close. I think I'm just going to take a couple of minutes for you to say what you can do now. As your quantum is going to be an open ecosystem of quantum hardware providers, software providers, and solution providers, along with Microsoft's own, we will enable the scalability via Azure Quantum, Azure platform, and we will make the hybrid computing available via the cloud computing notion. And you can start building your optimization solutions today and look at running them in future on circuit-based quantum algorithms as the machines start becoming available. You could start learning at LearnQC. These are some internal links, but search for the next part, right? LearnQC, quantum katas. Search for all of these keywords, and it should take you to the external links. You could download the QDK today. You could also look at Azure Quantum Preview Access, and you could keep yourself updated with the Microsoft Quantum blogs. And yeah, have fun and start learning, folks. And that sort of brings me to the end of this talk track today. Back to you, folks.
Thank you so much, Mom. Like I literally learned in depth a lot of things, and I can't wait to try out Q Sharp as soon as possible. We actually have a couple of questions from various students, so I'll ask to you. So, will quantum computing have a major effect on cybersecurity because of its efficiency? Yeah, is there a chance that the quantum computers can be used to break many effective algorithms like RSA? So, is there a threat to cybersecurity?
Yeah, so there is, and this has got nothing to do with efficiency. This is fundamentally because the RSA algorithm, so the algorithms that we use today is based on a fundamental assumption, right? And the assumption is if I give you, it is very easy for you to multiply two prime numbers today on a classical computer. Doing multiplication is easy, but if I give you a large multiplication of two large prime numbers, then finding out the original two numbers from that multiplication answer is an extremely difficult problem. That is called as prime number factorization problem, right? Given a multiplication, can I find out the large prime number factors? And that answer is no on a classical computer. The larger the number, the more difficult it is. And that is why you see the RSA key sizes increasing. So it sort of starts matching to your computing machines, right? So it says that if the computing power is increasing, which is sort of going to be in the hands of maybe a hacking community or somewhere, you just increase the size of the key so that the time it takes for them to create those factorization is exponentially increasing in few million years or something like that. That is the base. Now, on quantum computers, there is an algorithm called a Shor's algorithm, which was developed way before even the quantum computer came into reality by an MIT professor called as Professor Shor. That algorithm gives you a path to figure out an answer for prime number factorization using quantum computers. Basically using quantum Fourier transform, right? And that is why we think that it will fundamentally breach the RSA protocol, because now you are not really dependent on how big is my key size, because irrespective of your key size, if you have got good amount of qubits, you will be able to find out the actual prime numbers, and that breaks your security protocol. That is why availability of a quantum computer is a threat to cybersecurity. Yes.
Okay, so means in general, it's like with course of time we saw that storage isn't a problem, but now because quantum computers are there, now computation isn't much of a problem for us. Is it something
It
like that?
will still be no. So quantum computers is not at this point replacement for all computing power, and like that is what I was mentioning, right? It is not going to solve all problems.
Right.
For all you know, there are a set of problems that we solve very efficiently in the polynomial space on classical computer. Quantum computers will be overkill there because you know the deterministic ways of solving those problems optimally on your classical machines. So you think about quantum computer as addressing a problem which is in the non-polynomial or an exponential scale. or something that becomes exponential when you add a feature or a parameter into your problem domain mix, and you have a good shot at solving this more optimally on quantum computer. Uh, the near future quantum computers are not going to be big data solvers, which means that it will still operate on limited amount of data, but the algorithms are going to be different. So, like for example, say if you have got a machine learning problem, quantum computer is not going to dramatically speed up the ingestion of data. No, that still has to happen on a classical computer. But if you are doing an optimization solution on machine learning, so like for example, if you're trying to apply something like a support vector machine to your data set, then that particular piece of algorithm can probably be more accurate on quantum machine. So you will take set of data, move it there, represent the problem on quantum, run only SVM on a quantum machine and bring the result back and take the flow again on a hybrid standard classical computer from there. That is why I said it's always going to be a hybrid model to start with.
And the next question is that have we reached a point where quantum computing has been used to solve real world problems?
Yeah, yes and no, right? So, for example, if you are looking at optimization problems, which uses something called as quantum-inspired optimizers. Now, in all honesty, this quantum-inspired way of writing code came into being because the quantum hardware started becoming available. But now we are figuring out that for the optimization problems alone, there is no real proof that quantum hardware is the need of the hour. You change the logic, you change the algorithm as the way you have envisaged your quantum hardware and run it on the classical machine, you probably get the similar kind of speed up or a similar kind of accuracy boost. So that is your low hanging fruit. But there are also set of problems, like for example, the precision medicine kind of, or really risk modeling. Now, those problems will really need a circuit-based quantum hardware, and to run a real production scale problem on that those hardware are not available today. So you will have to sort of reduce the problem style to a POC kind of situation and then run it on the currently available hardware. But guess what? That is also going to be an important step because if your algorithm involves or needs qubits more than say 50, then you don't really have a way to check the accuracy of your algorithm on a quantum hardware. How do you know whatever you written is giving you the right answer? Because the answer is probabilistic on a quantum hardware. So how do you know what you wrote is the right code? You will have to downsize the problem and run it on the simulator first to see whether what you expected in the real world at a smaller scale and the answer, the algorithm is really giving you that answer before running it on a large scale machine. That is why I think the development has to start today. It is not a field which is easy to enter, and hence, you need a lot of this understanding built in, the practice built in to write the algorithms. So you can't really wait for developing your first good algorithm when the production scale quantum hardware is available. That has to happen now. But yeah, we are looking at probably more than 5 years to run the first production use case on a circuit-based quantum hardware.
So, first, with respect to students and career, is quantum computing a path that one student should take? Because of the high strength of engineers that India produces.
Yeah, so this is definitely a competency to build. If you are looking for a job in next 6 months, that is not the right field to pursue, honestly. But if you are looking at eventually building a career on quantum, if you are starting career and eventually want to be a quantum computing professional, you can definitely start building the competency today. I think the mainstreaming is about 5 years away, but we will take that much time also to learn and get professional there. Right? So yeah, that's how I look at it.
Okay.
Okay. So right now, like, can students start pursuing research-based work in quantum computing? And if that's so, how can we start?
Yeah, so there are a lot of internships, right? I think a lot of players are offering internships today for the students on quantum computing, including Microsoft, IBM, Amazon, even the Canada-based startups, INQ, Honeywell. I think a lot of people are offering internship work today. Unfortunately, a lot of internships are not happening in India, right? So that is the fundamental challenge. So if you're willing to sort of relocate, then keep looking at the career side, keep looking at the LinkedIn messaging that most of these companies nowadays leverage to find out the right internship opportunities outside India. Within India, that market is not yet developed. And I think India would probably pivot towards development and algorithmic development and PhDs and projects on, reducing the error code, making the debuggers more mainstream and stuff like that, which feeds into the development ecosystem rather than core capital intensive research, right? So take your pick. I think development folks actually would be the go-to persons few years down the line in India. So, that's where I think the India large-scale development ecosystem can move towards.
Okay, so like by what you say, like India is more like a development focused way rather than the research focused.
Yeah, I mean capital intensive, right? So, for example, if the research has to happen in error correct, writing the code on error correction for a qubit, I think India can take a good shot at it. But if we are really talking about developing a new methodology of realizing the qubit, that can become very capital intensive process. And most of the OEMs have their research centers headquartered in US or somewhere else, right? So I think that is why the internships are not based in India. At least that's what I am sensing right now. I mean, given the COVID challenges and given the fact that a lot of people have realized that remote work is a lot more productive than you could think about, I think those realities may change. So keep your track on, keep focused, and keep looking at the websites. But at least for now, that's the reality that I suppose.
So, what is the principle that you have followed till date, that because you have been into dream companies that you had very higher positions?
Yeah, I just got lucky, folks. I mean, I did not really follow any methodology per se. But one thing that I can sort of would like to leave you all with is keep learning. I think, keeping the student alive in you is a key because we are in a field which changes almost every day. If you are passionate about learning, that will come through, and it also helps you build long-term careers and pivot quickly because you are so into understanding and grasping. You are not letting that muscle go weak, and that helps to build longer careers, I would say, and staying relevant and essential in the tech field.
Yeah, totally agree
Thank you
with it.
so much, ma'am. Yeah.
Yeah.
Thank you for joining us today. Thank you for giving your time for us. We
All
learned a
well,
lot.
thanks, folks.
Yeah,
Thank you so much.
Bye. Take care, all of you.
yeah, thanks.
Thank you.
And thank you so much for your subscribers and listeners. Thank you so much for taking time out and
It's our
hopefully this
pleasure.
was good for all of you.
It was our pleasure, ma'am. We learned a lot. I'm going to rewind the entire session later on.
Sure. Okay. Bye. Take care.
Yeah.
Bye, ma'am. Thank you.